For those of you who haven't met me, my name's Dan. I'm the biochar facility manager. So this is the biochar facility. This space and everything out here on this side, what we're doing is taking in waste wood and we're making charcoal. We call it biochar when it goes in the soil. A lot of interesting biochar videos already produced online. We're going to do a biochar inoculation class this summer, so I encourage you to come out to that. I came on as a subcontractor when they were building this facility. I was working for a company doing radiant heating systems. So what we did is we put in the tubing here on the floor that's keeping us warm right now, and we interfaced all the biochar equipment with the heating system out here. So that's when I got really deep into the control side of things. I played around with controls at that company a little bit, but when we came out here, we built a box in there. I bet we've got 16 relays and 20-some pumps at this facility, and thermostats and controllers all over the place, and it's really turned into kind of a Frankenstein of a experiment at this point, but you guys can make sense out of it and copy what you need to on your farm or whatever it is you're doing. Can I ask you guys what you plan to do with this class? Maybe even ask you what you think this class is going to be about. What do you expect to get out of this class?
Yeah, I was hoping to learn or see some examples of electronic or temperature controllers or like humidity controllers for maybe your greenhouse to turn the fans on, or to maybe even a switch to feed your chickens, some sort of automation like that would be cool.
Yeah. And yeah, we talked some home automation, greenhouse automation work.
Home automation, irrigation systems for greenhouses and raised beds, and monitoring systems for water and electrical.
Cool. You guys?
Yeah, just basically get a little foundation on some of the various controls that can be used to make up systems, kind of like what you're referring to, greenhouse systems and whatnot on a homestead, farmstead, and basically, to be able to automate a few things and utilize maybe some DC voltage when possible, using the solar panels.
Yeah.
Kind of some off-grid electricity. So, just kind of more hands-on, like what looks like you've got going on here.
Okay.
Is what I'm interested in.
So we did a workshop, when we've got the videos online now, of small solar. So like very small solar battery backup systems. And part of the reason why we did that class was to preface this class. For anybody who's interested in doing some remote monitoring systems, we decided that we needed to talk about remote power first. So I'm happy to talk about solar as much as anybody wants to. We started the Repair Cafe, and that's a workshop where we just bring in volunteers that teach people how to fix things. And I have a gas oven, and what I thought was the broken gas valve, I thought it was the little element. I didn't really know how to troubleshoot it. I spent a long time troubleshooting that stuff, and it was all good. Everything was good. And then I got into actually looking at the control board. I thought, shoot, what am I going to have to do here? I've got like what I think is a $20 part, and I'm going to have to buy a $500 oven. I popped off the control board and just took my meter out, just casually, using my continuity tester to see if like a relay had gone bad or something. And it was so simple. It was a broken solder joint, and it's a $200 control board on a $400 oven. Most people would say, $200 control oven, let's throw the whole thing out. It's not worth it to fix it. Yeah, it literally took me 5 minutes to solder that thing and put it back together. And that, to me, was really inspiring. I want other people to have that kind of confidence, too. I had a similar story when I bought a welder from a friend of mine who said, I got a broken welder, you want to buy it? And I thought, oh, what's wrong with it? And he's like, speed control, I don't really know. I just got online and I Googled what's wrong with my welder, speed control, and I bet half a dozen other people in the last 10 years took it upon themselves to write about that problem. I found out it's a $5 transistor, found it on the board, pulled it out, soldered it back up. I got a $550 welder for $105. What we're going to cover today is pretty broad. We're going to start assuming that everybody knows nothing. We'll talk about circuits and being safe, and want everybody to be comfortable with a multimeter before we leave. Reading labels on all these little components, and sizing switches and sizing motors and wires and all that. We're going to at least recognize some components so that when we start opening up boxes, we'll at least be able to have a clue about what's going on. So it sounds like most of you guys want to know about some of the ready-made controllers out there. So we'll spend a little bit more time on that. That's one What I was going to reserve is the second half of this class. A lot of this stuff we've actually put together from junkyard parts. That's something I'm real proud of. We'll learn the vocabulary so that, when you go online and look for resources for further education. We are not going to talk about very inaccessible control programming. I was not planning on talking about IoT. We're certainly not talking about automation that replaces people, puts people out of work, or makes us lazy and not pay attention to what we're doing. Plenty of that out there. Turning a fan on. There's no reason why you need to drive across your 20-acre farm to open a valve if you can, have a timer do that for you. Let's take a look at this. Has anybody seen the FarmBot? Now, I don't want to pick a fight here, but this is a $2,400 4x8 raised bed. What we're talking about is basically a computer-controlled CNC gardening machine. Some people may be attracted to that. I, for one, want to go out and look at my plants. This is for somebody. Literally, what you do is you prepare your bed and you build this machine. And then you go inside and you get on your computer and you say, I want a kale plant here, drag, click. I want, beets over here, drag, click. And then you press play. And then presumably you can walk away until it's time to harvest. Yeah, it's a little goofy, and we're not going to talk about those systems. So you're in the wrong place if you want to learn about the FarmBot. Here is my wood stove at home. I have a water heating system in this wood stove. Okay, so what I did, I welded a stainless steel tube that's actually inside of my firebox, and I pump water off of my water heater, off the bottom of my water heater where the cold is incoming, and it goes up through the box, and then it comes back down, enters just a hair above where it came in. I've got it set up with a differential control, differential temperature control. This is the same kind of controller that they use on most solar thermal systems, where I look at the temperature just right on the backside of that, and I look at the temperature down in my water heater, and then I say, okay, is it hotter now up top than it is down low? If it is, turn the pump on, and let's start grabbing heat and dumping it into my tank. It took a long time to get this set up and learn sensor placement and all this. It's great, but it does not work when the power goes out. And it is a process where I have to go and I have to manually drain it so I don't create a bunch of steam. And it's actually become quite a bit of a headache to manage it. Not only just the controls, but I've got a big house that I heat exclusively with wood, and it does rob a little bit of heat, a little too much, especially like last week, I'm definitely not running it. So maybe a better option, instead of getting into complicated controls, is just do the thermosiphon system, where the heat actually just goes up into a tank. Hey, and then you're gravity draining out of that tank to do any hot water chores that you have. It's perfect. At my house, I was a little smug, and I wanted my water heater to stay down in the basement. I didn't want to see a water heater sitting up on top of my living room. So you go through great lengths to make that happen. That's just an example of a passive option. You guys got any ideas?
The system to support the system to support the system.
Yeah, exactly. One thing we do out here in our greenhouse, this is a funny greenhouse. It's almost opposite of other greenhouses in the area, because what we do is we keep the greenhouse inflated almost all the time. We have some inflation fans that keep the roof and the sidewalls inflated. They stay on 24/7. And then there's gable vents and there's in walls that have inflation fans on them. They're inflation fans that blow up a plastic bubble. And when it's hot, those fans turn off, and the gable vent and the inflation and the side vents fall down. And then we have this passive cooling thing where air can come in through the sidewall and vent out the top. Now, that's great. In the summertime, we're still running the fans all the time. This is a greenhouse that is made for the winter. That's an option that's a way that we can use passive cooling. Instead of most, I think, traditional greenhouses are going to be kind of a rigid construction, and they're going to have fans that cut on in the summertime to cool. So, that's just a couple of different ways we can do it. I'm not sure which one is the more passive option, really.
That picture on the right looks like just a copper tube wrapped around and hooked up to like a 15-gallon stainless steel drum or something.
Yeah, looks like it.
And it will just the heat flowing through that coil will cycle the water around.
Yeah, it's called thermostat. Yeah.
The tubing has to be big enough, though. That doesn't function very well when the tubing's small.
Oh, right.
And the other thing is, there's a big difference between the temperature on that stovepipe and the temperature in that firebox. With failure, the safety factors improve with the one on the right, with the thermosiphon, because it doesn't get that hot. I mean, it gets plenty hot for the water, but it doesn't get turned to steam, like instantly.
Yeah, if the power goes out for 5 minutes and I'm running my heater system, I'm going to be blowing off the steam relief valve. And it's a mess.
Yeah.
You know, I could build a system upon a system. I could have a battery backup for that. Or I could have some sort of power sense. If I see the grid go down, then I can close the solenoid valve and then drain the whole thing down and set that up automatically. I mean, there's options. It gets complicated pretty quick. Broad definition of a circuit, you've got a power source and some kind of a switch that switches a load, and then ground. And then ground is how you complete that circuit, right? So here's a really simple circuit. For our purposes, we're not going to really get much outside of talking about the outlet on the side of your wall. I mean, we're not going to talk about much power generation or anything like that. But this outlet, power basically comes out of the line side on your outlet, comes over your switch, lights up your light bulb, and then this is the neutral line, so this is going to return back, and essentially you make a circuit when that returns back. Theoretically, it goes all the way back to the power plant. It gets re-energized and comes back to your house. This is just going to basically show a picture of the circuit and where connections are made. And then there's the schematic of the circuit. Now, most of the time, what I do is some sort of a hybrid of these. I think anybody that's been formally trained in this is going to look at my stuff and just say, like, I don't know. But, it works for me, and it gets the point across to people that do look at it. So I use a schematic when I'm trying to design and understand the function of a system. And then a lot of times, if it's anything that I haven't done before, I'll actually sit and draw out where each wire is going to land. And then I'll just cross those off as I install. I'll just say, okay, I got that one. If it starts to get real loopy and messy. This is a ladder diagram. This one probably at first seems the most non-intuitive, but in my experience, the ladder diagram is the way to draw a circuit. It really helps you understand the series and parallel nature. Series is where you have flow from this point to this point. In order for power to get to this point, it has to go through here. Let me draw that a little more clear. Let's say you've got a battery right here, and you've got positive and negative. This is a series circuit. You're going to go out. You're going to have like a light bulb there, a light bulb there, a light bulb there, and then it's going to come around to ground. That's series, right? The difference in a parallel circuit is here. Say that's positive. You're going to have like this. 3 light bulbs to do that. Does that make sense to everybody? Okay. That's pretty important before we go on. So, in this case, if you have a switch right here, then you're going to switch power off to everything, or you can individually switch each light bulb. If you put a switch here, you're going to switch off everything. If you put a switch there, you're going to switch off everything. If you put a switch there, you're going to switch off everything because you're breaking that circuit. It's just like the Christmas lights. Everybody's heard about the Christmas lights. The old ones used to be in series. If one goes out, then the whole string goes out.
Oh, yeah.
Now they wire them in parallel, so you don't have to worry about that. That's where you need that extra third wire. What you can see here is a couple of different series parallel circuits. These, are basically parallel circuits. This is in series with this. Does that make sense? You can see that on a lot of the little drawings that I made. This is a pictorial diagram. A friend of mine is doing some installation work. You can see just the difference here. It's pretty stark. Okay, you've got this right here. You've got that. Let's land that wire exactly there. Let's land that wire exactly there. It kind of shows you exactly where to put each wire. And you can come through, and that's what I was saying, where you can, as you land wires, you can come in and cross them out as you go. Now, you can do that on these ladder diagrams as well, but it's not quite as clear. Let's talk about some switches. Who knows what that is? It's called a rocker switch. Okay, now you know what I'm asking.
Toggle.
Toggle.
Rotary. What is it? Contact.
Micro switch? Yeah, I would have called that a reed switch. This is a little harder one here. Float switch. Now I got all kinds of switches over here. Here, I'll just pass them out. Y'all grab your multimeters. All right, you guys all have some switches now. These are all random switches. Most of these switches came from the junkyard. That switch came off of, I swear, I think that was a hot dog rotating machine. Yeah, nice stuff. You know how much I paid for that? Probably like less than a nickel. That came out of a dry cleaning machine. And these guys have the dishwasher float switch. That's actually a float switch right there that he has. Dishwasher. You guys have a float switch too.
This says it's a thermostat. I don't know what it is.
Yeah, so with that, those kind of switches, you'll see them on a heat pump or like sometimes in a water heater pan. They go in the condensate pan on a heat pump. And what that will do is actually cut off your heat pump. So most heat pumps have a condensate drain pan of some sort. And they have a pump that'll pump out the condensate somewhere else. And if that pump fails, then your pan will fill up with water. And instead of flooding your basement or wherever your heat pump is, that thing will intercept your thermostat and tell your heat pump to cut off. So that is they call that the safety switch. Now that you've seen that, you're going to see them everywhere. Do you guys know single pole, single throw? Yeah. So his switch, if I was to draw that switch out, it's just going to look like that. Double pole, double throw. When you flick that switch, these two are actually going to move at the same time. You're going to go chook, 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 right? Down here, this is going to go chook, chook when you throw the switch. Is that the slider? Yeah, I tell you what we actually use that switch for is on our system, we've got some temperature displays. We did some troubleshooting a couple of years ago, and we bought a bunch of those, and we have 2 leads coming out of the middle of those going to our displays, and then we have a thermocouple on each side of those, right? So that we can switch between thermocouples. That switch looks like this. He's got the...
So the center position is off.
The center position is common.
Common?
Yeah. So what you're doing is, and the center position on this is common. When you flip the switch up, you're joining these two. And when you flip the switch down, you're joining these two, right?
Yeah.
So what we've done is we've got a thermocouple that comes in on this. With thermocouples, you have to switch both the positive and negative. And we've got a thermocouple up here. This one reads the front of our retort, biochar machines. This one reads the back. So if we need to see what's going on with the back, we'll come over there and we'll just flick that switch. And just for a second, we can see the display on the back, right?
Let you use one display for 2 thermocouples.
Yeah, we can get a $10 thermocouple, and those are nice displays out there. They're $150 a piece, so we can just switch around. Now, real, I think, control guys will probably tell you that that's not, it's not incredibly accurate. You're going to lose a little bit of accuracy on your thermocouples. For us, I mean, we're not in that kind of accuracy range anyway. Yeah, if we're 10 degrees one way or another, we're fine. Switches, some are normally open and normally closed. Normally closed refers to its resting point. That means in this normally closed position, power is going to move from here through that normally closed contact. Something has to change in order for it to go out that normally open contact. Okay? Same with the button switch. They have normally open and normally closed buttons. Over here, there's a button on our practice board that's actually a normally closed button. But that'll make sense here in a second. And then there's momentary and latching switches. Latching means that you flick the switch and it stays put until you activate it back somehow. Momentary is like a button switch where you press it, and it's only when you're pressing it is that switch activated, right? So I know that there's some toggle switches in there. One side it's a latching, and on the other side it's momentary, right?
That's what this one is.
Is it? Okay, so how you would draw that switch, that's the, that switch has 3 positions. So you would call that switch, if you were to go and you had to go buy one of these switches, right? Like say that switch failed, it's in your blender or whatever, and you need to get a new switch. You're going to look for a switch that looks like this. On, off in the middle position, and then on, and then put parentheses around it. Latching, on, momentary on. I know some of you guys have done a 3-way lighting switch. When you Google how do I do 3-way lighting switches, you get all these diagrams that are just wires going everywhere. It just looks like spaghetti, and then you're set off by it. You look at it and you say, oh my God, am I really I'm getting in over my head. I should call somebody. But instead, you could actually look at this as drawn in a schematic form, and it's wildly simple. Look at this switch. Here's a three-way switch. We're going to call that a single pole double throw switch. This is what happens in your three-way lighting circuit. You've got this on one end of the room and this on another end of the room, and your light's up there in the ceiling. And you flip that switch, and now power does not go to the light, right? But you walk over to the other end of the room, and you flip that switch, and now power goes to the light. See how simple that is? Like when you draw it out in a schematic form. All right, so I was getting ready for the class. This was actually just yesterday. And finishing up this PowerPoint, I'm sitting at a little coffee shop in Weaverville. And there's a guy that I recognize as somebody that comes to a lot of our classes. And I don't remember his name, but he sat down at the table with me, and he's like, I've got a beehive. And we had some really cold temperatures. I want to have a data logger that can read the temperature at 4 different places in my beehive. And I want to be able to see, like, whatever, what I'm doing, is it having an effect? If I insulate the top, or if I put a box around it, or whatever, what kind of results am I actually getting? How cold is it outside versus how cold is it inside my hive? And what he wants is, he wants something that can look at 4 different temperatures, either at once, or he can just walk up there and select between them, right? So Omega, the same company that does our temperature displays, does have a little handheld unit that has 4 thermocouples that come out, and it's really nice, and it can read 4 different temperatures at the same time, and it can data log all 4 different temperatures. Now that machine is somewhere around like $400, which, if that's worth it to you, then that's obviously that's the way to go. One way that he was looking was like, okay, how can I get this down? How can I get the cost down on that? I don't necessarily need to record all 4 at the same time, right? So we started looking at switches, and we said, I came across this last night. That monster there, that's all in a single switch, but that's the way to do it. This is a 4-pole, 4-throw switch, but it has 20 pins on it. 4 different positions, right? See these little horseshoe-shaped sliders? Okay, in position 1, these sliders are here, right? The black pins are common, okay? So that represents the same as the thermocouple switch that I drew over there. If I was sending these out to a data logger or some sort of display unit, then I would say positive out, negative out, right here on these, okay? Does that make sense? I'd put incoming positive for the thermocouple number 1 here. Incoming positive for thermocouple number 2. Incoming number 3. Incoming number 4. Okay? Outgoing is up here. So what we could do is actually take the switch, turn it upside down, and we could have a wire that goes from here to here. Okay? So we've got incoming number 1. Makes this path when it's in the leftmost position. So if we want to read number 1, and out, right? Okay? Now if we take that switch and we knock it over 1 time, like as in over here, see this path? Incoming number 2, comes around, does that little horseshoe, comes down. These 2 pins are actually already connected. Comes down here. Goes out and out, right? So we can do that. We can have the positives and the negatives on this side. We can switch that switch around. And as far as I know, that's the only way that I could come up with to look at 4 different thermocouples at the same time.
If you say looking at 4 different thermocouples at the same time, you mean have the ability to...
Yeah, on the same unit. That's right. Yeah, I'm sorry.
Hey, what's a thermocouple?
That's a temperature sensing device.
Okay.
Yeah, so that's your sensor,
Yeah,
basically.
Gotcha.
So look right up there above your head. We got a couple of little thermocouples, and there's RTD sensors.
You're not using a rotary switch?
Yeah, I think there is a rotary switch design.
I've worked with them where you just got a center column position. And depending on how many discs is how many poles you have. So it will just make contact as you rotate it around.
Yeah, now that would work if we had a common across all those thermocouples, but remember I said we have to switch the positive and the negative.
That's what I'm saying, use the 2 disc, use
It's the same
the
thing.
2
as rotary.
leads.
Same stick.
And it would be
It's easier
rotary
if
instead of linear.
Yeah.
Click instead of slide, so you
Yeah.
can point to.
Okay. Well, everybody grab your multimeters and switch it over to the little symbol that looks like this. Yep, you're all set.
Okay.
So,
2.3.
well, so what we're looking for is just continuity. That little beeping sound when we have electrical continuity between these 2 points. Anywhere that's basically going to conduct electricity enough to make these go. Okay, so that switch is open right now.
Okay.
Oh.
Now it's
Yeah.
closed.
Ah.
Right?
Oh.
Yeah.
Gotcha.
Yeah, so you can go around and test all these switches. Is this switch normally open or is it normally closed?
So you can,
You know, you would have to test these little leads to find out.
and then you can find out if the switch works or not either.
Yeah, you can find out if it's working,
You
right?
got all these from junkyards. So.
Yeah, exactly.
Oh, yeah.
Yeah. Yeah.
Yeah.
So mess around with these switches, man. You'll make them work. Let me strip those leads and you can do that. Look right down here. This is a single pole, single throw switch. So all we're doing is just breaking power between here and here, right? So what I've done is had power come in. Power comes in and hits this switch. So let's play around with this a little bit and see if we can't figure out where power's going. All right, so you want to see, let's check first to see if this switch is on or off. Ignore the fact that it says on. Okay.
Okay, so power's going through it.
No, power's not going through it. Okay, power's going through it. Let's measure it off the plug. Okay, so that's the line side of this switch. Line side is the one that's usually energized all the time. Okay, load side of that switch no longer has power. Now it has power. That wire comes over to here. When the switch is on, here, right? Okay, anytime you're wiring up an outlet, you're going to have a brass screw and a silver screw. The silver screw is where you land your neutral. That's like your return line, if you think of it that way. And the brass screw is where you're going to land your line, your black wire, the live wire. There's a couple of different ways people will talk about it. All right, power comes in here. We know that that's the line side of this switch, right? Okay, so we know that's always got power on it. Let's see what else always has power on it. Down here, right? Also down here on this, except you actually can't get to those terminals, but, right? So if you look at the drawing, you can see that that point right there is what we're measuring when we do that. Now let's see, now we always have power on that, so that's down here. This is our three-way switch. Remember when I drew the three-way switch diagram where, you know, power can either go this way or you can switch and have power change, right? So you can sit here and mess around with this. Black on these three-way switches is the common. So there'll be a black screw that represents that spot. And then over here on this one, there'll be a black screw that represents that spot, right? And then you can measure these other two to see which position the switch is in. So pull your light bulb off. You know, on a light bulb, this is like your neutral side, and then that's your line side. Okay? So measure right down there on that center pin. And let's see if this light bulb would be energized right now. Start flicking, flip one of those switches there. There it is. So now our light's on.
Does this even matter?
Yeah, well, look where it is on the schematic.
Oh, so it does have to be on,
Well, no, it doesn't.
right?
Power comes in.
Oh, so it can come.
Yeah, it
this
doesn't
way.
even, you know, that switch only controls this. That switch has nothing to do with anything else down the line, right?
So you have to pay attention to the labeling
Yeah,
for what is common.
yeah.
Because I've wired them up backwards and stuff and couldn't figure out why it wouldn't work. And it's because the physical location was different.
Yeah.
I just put wire here from this one to here in the same position. It wouldn't work.
Yeah, right on the, at the back of those switches will probably say something. It'll actually be labeled common. Yeah, sometimes it's real obvious, so they'll color it and it'll be black for the common. But
Problem I found, I'm trying to I understand all the electrics in my house. It's got a mess in it.
Or is there like something reducing the electricity going into that?
That is really depends on the current draw of that wire, right? Of whatever is downstream of that. So maybe. In this case, no.
This is a 14 gauge wire, it'll support 15 amps. This is a 12 gauge wire, it'll support 20 amps. So the fuse is sized for the wire that's connected to it, not what device is drawing current from it.
If you want to say like, okay, here's a single pole double throw switch right here. Let's try to figure out which side is common, right? You know, so imagine that nothing's hooked up to this. All right, we have no continuity at all here across any of these poles. So center position is off, right? All right, which one? No? No? Ooh, yes. Okay. So we know one of these is common. We still don't know for sure which one is. All right, flip in the other position. Not. Now we know that's the common. Yeah, right. Just by deducing.
in this position, and it was energized in this position.
Exactly.
It's the only one that was.
Okay, so what we basically have is a little three-way switch right here. It's a little selector switch that says, are we going to go this way on the diagram, or are we going to go this way? One or the other. In this case, we're going to go, I think it's this way, and we're going to energize this little reed switch down here.
So where was the line that it's traveling?
Right there, it's going this way. It's going up, and then it's going over to this single pole, single throw, momentary on,
Oh, okay.
latching off switch. And then it goes from there, goes over here to energize this relay, and then high voltage goes through the relay and turns the light bulb on. So we'll look at all that stuff here in a second, too.
Double pole, triple throw?
That is a single pole double throw switch. You know, where does it land? There's 2 places that thing can land. And the pole, you know, think of it, it's just like, oh, it's a pole moving. You know, let's move the pole. You know, so single pole, double throw. There's 2 places it could go. Now a double pole, double throw switch does this.
So the middle position doesn't count as a...
It doesn't count as a throw. Yeah. Well, we're ready for part 2.